This is 40 Days of Chemistry Part 14, and this time it's right back to the start to 9.2.1, Petrochemicals, Cracking and Addition Reactions. This is Part A of 9.2.1. And the first thing we learned about was fractional distillation. We know we get crude oil out of the ground, and it's a mixture of hydrocarbons. It's a liquid mixture of hydrocarbons, and we pump it into the bottom of the fractional distillation tower, and we also heat the bottom of the tower. And because we're heating the bottom, there's a temperature gradient. It's hot at the bottom and it's cold at the top. The heat at the bottom causes the fractions, or the different mixture components, to evaporate, and as they evaporate they rise up the column. But because there's a temperature gradient, that means the fractions will rise up to a point at which the temperature of the tower matches their boiling point, and thus they condense where their temperature matches their boiling points. Therefore the fractional distillation separates them based on their boiling point. But because for hydrocarbons the molecular weight is proportional to boiling point, it also separates them based on their molecular weights. And what you get is you get high boiling point, high molecular weight compounds coming out the bottom of the tower, and low boiling point or low molecular weight hydrocarbons coming out the top of the tower. The key thing to note is that it's a physical process. It's not a chemical reaction, it's a physical reaction. It's separating out a mixture based on boiling point. The next thing we learned was about cracking, and we learnt from the fractional distillation process we get a range of fractions, but not all fractions are in the same demand. For example, the high molecular weight fractions are in low demand, whereas the low molecular weight fractions are in high demand. Therefore they need to make more of these high demand, low molecular weight fractions. And how they do that is cracking. And cracking is just a fancy word for decomposing hydrocarbons. And what we do is we get some larger, slightly less useful hydrocarbons, and we do the cracking process to make smaller, more useful hydrocarbons. In this case we've cracked the decane to make octane, which is the main component of petrol, so it's a fuel, and also produced ethene. And ethene is a very important chemical because it's the raw material, it's the basic precursor for most petrochemicals. So those are two very important chemicals. It's also important to note that when you do cracking you get one alkane and one alkene. There are two types of cracking. The first one is steam cracking. They basically pass the mixtures, or they pass the high molecular weight fractions into hot pipes with steam, and that the heat and the steam causes them to crack into smaller molecular weight hydrocarbons. Now that's often used not so much for very big fractions, but it's often used to crack the propane fraction of natural gas. The propane fraction is less useful, but you can crack that down to methane and ethene, which are very useful. Catalytic cracking is often what's used for normal crude oil hydrocarbons. Use a zeolite catalyst. The fact that it's a catalyst increases the rate of reaction, therefore decreases the temperature and the cost needed. And for crude oil fractions, usually about 500 degrees with no air above 1 atmosphere, and that 500 degrees is lower temperature than steam cracking, which is between 700 and 1000 degrees. Cracking is a chemical process, it's a chemical change. In the past HSC ones they asked what are the physical and chemical processes used to make ethene, and you have to go through the fact that you use physical processes in the distillation, and then they use cracking to get the ethene later on. So why do we want ethene? And the reason we want ethene is because ethene is an alkene, and they can undergo these things called addition reactions. But before we look at addition reactions, let's look at what alkanes can do. Alkanes don't undergo addition reactions. They undergo what's called substitution reactions, and they've got to do that in the presence of UV light. That's because the alkanes aren't very reactive, and the UV light's there to provide some activation energy. These reactions are slow as well. So as an example, here's ethane. That's an example alkane, and it's reacting with bromine, Br2 liquid. Now you've got to have UV light shining on the reaction for this to happen, and what happens, it's called a substitution because one of the bromine atoms substitutes one of the hydrogen atoms from the chain. So this bromine here has jumped on to the alkane, the other bromine has combined with that hydrogen that came off the chain. So we've got ethane plus bromine turns into bromoethane plus hydrogen bromide. However, alkenes undergo what's called addition reactions, and you need to know what an addition reaction is. You need to have a nice definition of an addition reaction. It's where a small molecule adds across the site of the double bond. They don't need an input energy, and they're fast due to the fact that alkenes have a reactive double bond. You don't need to say this bit, this is just for information, but you do need to know this underlying bit, what an addition reaction is. Someone asked me the other day, why is it that the carbon-carbon double bond is so reactive? It's mainly because it's got a high electron density. You've got 4 electrons all closely packed together, and therefore those 4 electrons would much rather be in single bonds further apart from each other. That's why it's so reactive. So an example of an addition reaction, we've got ethene here, which is the simplest example of an alkene. It's reacting with bromine as well. We don't need input energy, there's no UV required. And what happens is that the whole molecule adds across the double bond. So there's no other products, there's only one product. And when we say add across the double bond, the bromine molecule splits in half. Half of it joins onto one carbon and half to the other across the site where the double bond used to be. So we've got ethene plus bromine has turned into 1,2 dibromoethane. And in general, there's a general addition reaction. What we've got in the general addition reaction is the fact that any alkene molecule, and we've got this double bonded carbon here making an alkene, we've got Ra, Rb, Rc and Rd. That just means you could have anything attached there. This could be chlorine, this could be an oxygen attached to another chain of carbons, this could be a huge long carbon chain, this could be a hydrogen. It doesn't matter what they are, the most important thing in addition reactions is the double bond. And when you react an alkene with another molecule, that molecule splits and adds across the double bond. So let's look at where the electrons will be. In this double bond you'd have 4 electrons. It's not really drawing them on there, is there? There's 1, 2, 3, and 4. Within this XY molecule, this bond here would have 1 electron from the X and would have 1 electron from the Y. And what's happening in this situation is that this double bond here is splitting, and these 2 electrons are breaking apart from each other to make new bonds. And what you've got, one of those electrons ends up bonding with the X molecule. So let's draw it in there. One's bonding with the Y. It doesn't really want to draw pictures today, unfortunately. So there's that Y bond with 1 electron from the Y and 1 from the alkene. And here's the X, 1 from the X and 1 from the alkene, making 2 new bonds. And that's what happens in an addition reaction. You get the alkene reacts with the molecule to make 1 new molecule only. Addition reactions number 2, there's a whole range of different types of addition reactions. The one that have been mentioned in the HCC in the past are the following. You've got adding hydrogen, which is called hydrogenation. You need a nickel catalyst for this. So you have an alkene reacting with hydrogen to produce an alkane. In this case, ethene reacting with hydrogen to produce ethane. Note the hydrogen adding across the side of the double bond. You're adding halogens. This is called halogenation. In this case, adding chlorine. So ethene plus chlorine turns into 1,2-dichloroethane. The chlorines have added across the double bond. Hydrogen halide is called hydrohalogenation. We're adding something like hydrogen chloride, which is a hydrogen joined up with a halogen. You've got ethene plus hydrogen chloride turns into chloroethane. Once again, the HCl has added across the side of the double bond. You've got adding water called hydration. You need a sulfuric acid catalyst for this. That's why I've got H2SO4 above the arrow. When it happens here, the water splits in half into 1 hydrogen and 1 hydroxyl group, in this case making ethanol. An important little tip to remember whenever drawing OH groups, it's the oxygen that bonds with the carbon, so make sure you've got the bond attaching to the oxygen, not the hydrogen when you're putting a hydroxyl group on. And the last type of addition reaction we study in the HSC course is when you add alkenes with alkenes. This is called addition polymerization. You have N alkenes reacting with N alkenes to make a huge long chain. It's like a huge long alkane chain. They're called a polymer. Well, these are called the monomers. The 2 initial chemicals are called the monomers, reacting to form the polymer in an addition polymerization. And this would be polyethylene. Just be aware that ethene is the systematic name, but the common name or the accepted useful name is ethylene. Let's look at the bromine water experiment, one of the most important experiments in the course, looking at the reactions of alkenes and alkanes. One important thing to remember in this whole process is that water is a polar solvent, whereas alkanes, alkenes, and the halogen molecules, such as bromine, are non-polar. So what did we observe in our reaction? Well, what we had was we had clear alkane and a clear alkene, and we had our bromine water. We added the bromine water to both the alkene and the alkane, making sure we added the same volume to each. The dense aqueous bromine water sank to the bottom, and the less dense alkane and alkene floated on the top. Very soon after, the bromine started diffusing up into the alkene and alkane layers. And the reason for that is that bromine is slightly soluble in water because bromine is non-polar and water is polar. But at the interface, the bromine at the interface, basically it had a choice, I suppose you could say, of dissolving into the non-polar solvent, the alkene or the alkane, or staying in the water. So over time, because the bromine is a non-polar molecule, it tends to dissolve into the non-polar solvent, into the alkene or the alkane. So what we saw in the alkane example is the alkane started turning brown because of the bromine dissolving up into it. With the alkene, though, what we saw was a little yellow layer above the interface, a bit clear above that, and a short time later the alkene had turned completely clear. Both layers were clear, whereas the alkane, both layers were brown. And we need to explain what's going on there. So what's happening is when the bromine is dissolving into the alkane, nothing happens. We did this experiment out of UV light, therefore no substitution reactions would take place. Therefore the bromine just stayed in the alkane, staining the alkane brown. When the bromine did dissolve into the alkene, though, it started dissolving and then reacted. So this yellow layer here is where the bromine's first dissolving into the alkene, but then it's reacting and turning clear. And that's why after time, all the bromine has dissolved up into the alkene layer and it's all reacted. Therefore the whole thing is now clear because it's the bromine that gives the bromine water the brown color. Take away the bromine or react the bromine and that means you've got no more bromine molecules, so it's not brown anymore. So let's now look at some of the important conditions of this particular experiment, or this particular reaction we did. First of all, the independent variable, the only thing we changed in our experiment was the presence of the double bond, the alkene versus the alkane. The dependent variable was the reactivity, the alkene versus the alkane reactivity, and we determined that by the rate of colour change with the bromine water. The control variables are things we kept constant with the volume of solutions, the volume of reactants. The bromine water, alkenes and alkanes are all kept constant volumes, and we controlled the temperature. And one of the most important things, we had corresponding structures. To make sure it was a valid experiment, we need to make sure all the variables are controlled, and therefore we need to keep the number of carbons in the molecule and the shape of the molecule constant. All we changed was the presence of the double bond or the single bonds only. What other conditions did we take place? We had no UV light, so there could be no substitution reactions. The alkane couldn't react out of the presence of the UV light. We used either hexane and hexene, or cyclohexane and cyclohexene, because they're liquids. We could actually do the experiment with them because they're liquid molecules, and also relatively safe compared to some other alkene and alkane compounds we could have used. As far as safety is concerned, the alkene and alkane are volatile chemicals, which means they evaporate easily, and they're flammable, and they're also toxic. And therefore we used a fume cupboard, we used gloves and glasses, and we had no flames there, so we weren't going to ignite those compounds. The bromine water produces toxic fumes. It's also corrosive. So once again, we did the experiment in a fume cupboard, used gloves and glasses. I suppose you also we use low volumes. We use 2 mils maximum of any of these chemicals to keep it safe. And also, as far as safety is concerned, disposal, we stored these chemicals for proper disposal. That's that nice little phrase we can use. So what reaction took place? Well, we know that the alkene reacted, therefore we know it's going to be an addition reaction taking place. So we had our hex-1-ene, I've been calling it hexene all along, it's very bad of me. We had our hex-1-ene, it's a liquid, it reacted with the aqueous bromine water. The bromine had an addition reaction, it added across the site of the double bond, there's a double bond there, so half the bromine went to one of these carbons, half to the other. So we have one bromine there, there's all single bonds now, and the name of this chemical is 1,2-dibromohexane. Now, one note, and I think I've been bad at this in the past, I tend to say that the bromine water has been discoloured, but technically discoloured means changed to an unwanted colour. If you had white wallpaper and it turned yellow, that would be discoloured, it's turned to the wrong colour. In actual fact, what's happened is the bromine water has been decoloured, which means it has lost its colour. So please use the word decoloured rather than discoloured. Last page. Well, this is the experiment number 2, because sometimes we don't use hex-1-ene and hexane, we use cyclohexene and cyclohexane. And I actually prefer to use cyclohexene because, in actual fact, right in the reaction is much simpler because you can use this geometrical molecular structures when you're using cyclohexene. So here's our cyclohexene. It is a liquid, it is a hexagonal structure, and it's got one double bond. When you're doing structural chemistry, if you draw shapes and rings like this, it's accepted that at every corner there's a carbon, and that every carbon, when there's nothing else drawn there, there's enough hydrogens there to make up the 4 bonds the hydrogens need. So for example, this corner here, it'd be a carbon there, it's currently got 2 bonds attached to it, so there must be 2 other bonds, there must be 2 hydrogens attached to that carbon. It's reacting with the aqueous bromine water, and it's turning into this chemical here, which will be a liquid. It won't be aqueous, it won't dissolve in water because it's non-polar, and it's 1,2-dibromocyclohexane. Just want to slip back a slide to make sure. This should have also been a liquid, it won't dissolve in the water. 1,2-dibromohexane is also a liquid. But as we learn later on in the course, and this is mainly for the Year 12 students here, this is not really what's going on at all, because bromine water is a bit more complicated than just aqueous bromine. And that's because aqueous bromine actually reacts with water in an equilibrium reaction. And when bromine reacts with water in equilibrium, it forms 2 chemicals. It forms hydrobromic acid and hypobromous acid, HBr aqueous and HOBr aqueous. And it's actually this chemical here, it's actually the HOBr that's technically actually reacting with our alkene. And HOBr reacting with our alkene, undergoing an addition reaction, it adds 1 bromine to one of these carbons and a hydroxyl group to the other. What we get is 2-bromocyclohexanol actually. So we're actually not reacting bromine directly with the alkane or the alkene at all. And this is a bit puzzling at first because we've said the whole point of this reaction is it's taking away the bromine molecules and therefore it's turning clear. But in this equilibrium, this chemical here, the bromine's brown, but all these chemicals are clear. So looking at this, it looks as though all we're doing is taking away a clear chemical. So therefore, why is the solution decoloring? Why is it losing its brownness? That's because of something called the Chatelet's principle, which we're going to study later on, which relates to equilibrium reactions. If we remove a chemical from an equilibrium, the equilibrium shifts to try and make more of that chemical. So as we're reacting and taking away the HOBr in this reaction, as that concentration is dropping, the reaction is shifting to the right, so more bromine is reacting with water to try and make more HOBr. But as soon as the bromine reacts with water to make more HOBr, the HOBr immediately reacts with the cyclohexene and is gone. So this reaction keeps on going this way to replace the HOBr. The HOBr keeps reacting until eventually all the bromine has been used up because it's all tried to make HOBr and the HOBr is consumed over time. So that's why the solution turns clear. That's the actual real technical reason of what's happening. But as far as the HSC is concerned, if you wrote this reaction here or you wrote this reaction here, they're both accepted in the HSC exam. Lastly, what's next? So far in our 40 days of chemistry, we've covered quite a few focus areas. We've finished off the skills focus area. We've done the first half of petrochemicals here. There's going to be another half coming up soon. We've done biomass, we've done nuclear chemistry, acidic oxides, pH, acid theory, monitoring in the Haber process. There's still quite a few more things to go. We've got ethanol, we've got batteries, indicators, esters, AAS and ions. I'm thinking I might do that one soon. Ozone and CFCs, water testing, and the whole elective topic. So please, Year 12s heading towards the HSC, or Year 11s who are curious about any of these topics, please let me know which one you want me to make so I know which one to make next.